Well, here we go. Great. Good thing you're all here. But when we try to set, so why, anybody tell me why this line gives me an error? Yeah.
Because 2 doesn't exist.
Yep. I got B at 0, I got A at 1, and there's nothing at 2, right? Perfect. We can remove, etc. I think we are comfortable with all of this. Okay, and we already talked about this. Obvious choice for implementing the list ADT is an array. And let's keep going. We talked about this. Add, for example, we have to shift everybody to the right. Remove, we have to shift everybody to the left. So add and remove take big O of n time. And okay, at this point, before we talk about dynamic arrays, I wanted to introduce Lab 11. So let's go look at Lab 11 and see. Anybody started Lab 11 yet? Couple hands. Really, this is just kind of a return to, let's get back into some Java programming. We've really been doing a lot of thinking about runtimes. So let's just do some Java programming. All right, Lab 11, do this Thursday, anywhere on Earth. And you're also going to do some input checking. So we learned about exceptions like many weeks ago, but I don't think we actually had a lab on it. So now we're going to get some practice with exceptions. So here, basically, you are finishing off this software that's going to be used in a bike shop rental facility. So the software is interacting with a bike shop employee, probably. So there's some starter code, and there are 5 to-dos in the starter code that you need to do. And so in terms of grading, when we come down to the grading section, basically, you do each to-do, you get 2 points. That's how you get your 10 points. So let's take a look at this. We got Project 4 starter. Oh, that's Project 4, not Project 4. Lab 11. Maybe I don't have the Lab 11 starter. Let's just open it up so that I don't show you my code, huh? What are you going to open? Yes, perfect. So this is still how I open stuff in Eclipse, is by copying it in, because I do not know a better way. There might be a better way. I don't know. Anybody else know a better way? Know how to just directly put a directory into Eclipse? You do?
Yeah, I mean, you can find the source files in here, this file explorer.
And just drag them in?
Drag them in there. If you drag a zip folder there, though, it does a little bit different thing, but you can still do it.
If you do that method, though, you do have to refresh manually on the Eclipse side of things, otherwise it won't recognize it.
That's what I was like, Eclipse is doing something.
You can click on whatever, the new file.
Oh.
And then you can file.
Okay. File import. Import. Oh, yeah.
Neat.
And then you have to take the file right there.
File?
And it's called file system.
File system. Oh. Directory.
And you go folder.
Downloads. Well, this is perfect. This is me learning things. Uh-oh.
You just have to on the forward side.
What was that?
Or the folder.
Just the whole, open.
And select the file.
Oh. Yeah, I got to come to class today. It's perfect. Okay. Unfortunately, it's not, I wonder if it, yeah, that's all. Okay. So let's see, is this the one that has the to-dos in it? No, like reservations. Okay, let's just run this, see what's happening. So yeah, you can see I have this interface, and when I do something like, well, availability works, already implemented, but when I do something like listing, it says listing of bikes is coming soon, and so you are going to need to find the to-dos for that. And so there's some hints. Yeah, so for example, you're probably going to want to use the get method of an array list. We've got an array list, as you can see, I've got an array list here in that we're working with. And can anybody tell me what data type is our array list storing? It's not very exciting, it's just right there, but yeah. Exactly. Bike rentals, and those are something that we have defined in the bike rental file. So an object of our own creation. You do not need to change the bike rental file, but you may want to actually look at its methods, because you're going to want to call some of these methods. So take a look at that. Any questions, or anybody started on this and noticed anything weird or have any questions so far? Cool. Awesome. So yeah, that is lab 11. And now let's come back to today. Okay. All right, so here we are. We're back in array lists. And so as we've talked about a lot of times in this class already, arrays have a fixed capacity. But if we have an array that's full, and a lot of you have thought of this basically on your own, whether it was in assignments or in class, when the array is full, we don't have to just say, oh, we give up. Instead, we can replace it with a larger one. And there's a lot of ways that we can, a lot of words we'll use to describe this. So here, these slides are calling it a growable array list. We also often call these dynamic arrays. And so the big question, if we're going to implement one of these growable array lists, is how large should the new array be? So if we look back at our okay, we're done with bike rentals. Quick detour to bike rentals, but now we're back at day 30, and we're looking at our array list. So we start out with the capacity 16. That's just what the book has chosen. I actually don't know what the built-in Java array list capacity is, but 16 seems like a good enough number. And we get down to we're going to have a resize method. So, but when we get to our resize, how big should we make it? And it turns out that how we answer this question actually matters a lot for the runtime. And so we could, I think, two natural ideas are to increase the size by some constant c. So for example, it's 16, and I added my 15th element in, I added my 16th element in, and now I call add, and it's full. And how big should my new array be? Well, if I use the incremental strategy, then I choose some constant, like say maybe I increase it by just 5 every time. I don't know. I just chose 5, but I increase it by 5 every time. So, okay, it was 16. I increased by 5, so now it's size 21. I added my thing. I added whatever I was going to add in, so now it is 17. And now I call add 4 more times. It's size 21. That's as big as it's going to be. So then when I call add again to add my 22nd element, I'm just going to add, I'm going to increase the length, the array to be size, it was 21. We'll just write this down. So we were at 16, we were 21, 26, ... That's with C equals 5, right? That strategy makes sense? That's what we call the incremental strategy. Alternatively, we also have a doubling strategy. So suppose, again, I start with 16, but once I want to add my 17th element, I double. So instead of just adding some number, I double it to 32. And now I have a whole 16 to go, but when I'm going to add my 33rd element, then I double it again. So I don't add 16 because that would be an increment of 16. I've got to double it. So I go 32 to 64. So anybody know which one is actually used in Java's array list or the book's array list?
Doubling?
Yeah, it is doubling. And, well, do you know why?
Because if you did it with a constant function, it would just have to, it'd be calling way more time, or it would be calling more times than if you just double it each time.
Yeah, that's
an abstract list.
Yeah, that is an important part of the reason. And the reason is actually, in the end, let's see. So it turns out that in the end, if we use the doubling strategy, when we analyze the worst case runtime of the algorithm, it's going to, in the end, give us a big O of 1, we say amortized time to add elements, if we use the doubling strategy. If we use the incremental strategy, when we make the same analysis, we end up with a worst case runtime. It ends up being big O of n if we use an incremental strategy. And the reason actually it comes down to, it's because we are having to recreate the array so many times. So even if we make that C really big, so here we did a C equals 5, you might think to yourself, well, yeah, okay, that means we're going to have to resize the array every 5 adds. But even if I make C 100 or 1,000, then because we're doing this asymptotic analysis that's in the long-term growth rate, we're still going to end up with a big O of n runtime. Okay, so in this class, we want to just get an intuitive understanding of how do we make this analysis. Yeah. No. Yeah, so the difference is basically comes out, so tripling in the end is also going to be big O of n. Any geometric series is going to be big O of n. And the way that I like to, the intuitive way that I like to think about it, and you'll also see this language a lot, like in algorithmic analysis, is when we think about what we want to think about. So maybe we'll try to get an explanation and let me know if it feels convincing to you. So, okay, so we're going to think about our doubling strategy first. So here, this figure's from the book. In this direction, this is how many operations, so when we actually call add, how many operations do we have to do? Well, we have two cases. So this is number operations. So we have two cases. Either we don't have to resize the array, right? And we don't do very many operations. We just do a couple, like 3 or something. And so that's what all these are referring to. Anything that is small, that's one of those add calls that we didn't have to resize the array. Did not resize all these ones. And same with these ones. Can anyone tell me? Well, I guess, okay, and then these ones we did, right? Had to resize. This big guy, etc. Can anybody tell me? Oh, also, and this is the current number of elements. Hopefully that's not too small. I'll just make, which would also be size, right? If we call it our size method, that's what would be returned. So looking at this, can anyone tell me what that initial capacity was? Or if you have a question also.
Will the initial capacity be 1 and the doubles?
Yeah, exactly. So in our example implementation, our capacity was 16, but in this figure, the initial capacity was 1 because we had to take, it took us more time when we called resize. We had to do that at 2. So we knew that the capacity started at 1. Okay, so cool. That's helps me know that this figure is making sense. Okay, any questions about this labeling of like, okay, we had to resize at 16, we had to resize at 8, we had to resize at 4, etc. Yeah.
So do you resize when you fill up your array, or when you have a full array and want to push one more element into it?
When you, I guess I was thinking you have a full array and you want to push one more into it. It's possible that this reflects that you are leaving an extra one because, well, no. Yeah, it's when you're already full and you want to add one more in. So, for example, when you start with your array of 1, you add something in, something's in there, and now, oh, maybe we started with 2 because when we were at 2, we had to call resize, and that's when it got big. But sure. So we were at 2, it's full, we have to resize, so then it becomes length 4, so that's why this much time was taken. We add something in. I guess, okay. Yeah, and then we now have 4 elements and we have to resize again, etc. But in general, it wouldn't matter for our asymptotic analysis whether we did either of those strategies. Okay, so this chart is making sense. Okay, so now when we do our asymptotic analysis, basically what we're going to say is, okay, so I have some operations like at 16, at 8, at 4, at 2. I have some that take a long time, but I have a lot that don't take very much time. And so we often use the language of charging because we want to think about, in the end, we're going to do n adds, let's say. We're going to do n adds, and some of them take a lot of time, some of them take very little time. And in our asymptotic analysis, we're going to want to basically charge some of this big time to everything that happened down here. So it doesn't actually take, each one of these calls it really only takes that small constant amount of time. But when we're accounting for the total runtime, we are going to, which we would show is big O of n. Via amortized analysis. So what we say is that we charge this runtime. We charge some of it to this block here. We charge some of it to this block here, some of it to this block here, some of it to this block here, etc. And so when we're doubling, I believe that we can actually think of charging kind of like three. If we charge each one, let's make a better picture here. We can basically think of, so here there are going to be 8 blocks here, right? And so if I think of dividing this into 8ths and charging each one to one of these 8 blocks, then that's how I eventually get to this kind of overall rectangle, rather than, which a rectangle is basically a big O of n shape, right? Like if I think of, it's only taking me a constant, it's a bigger constant, like at each one, but it's still an overall constant that's being charged for each one, yeah. Exactly. So that's exactly what happens. Is that okay? So overall, over n adds. So let's say I call add 16 times. Over 16 times, it took overall big O of n time. And now I say, well then per add call, I'm basically dividing n by n. And so in the end, I get something constant. And that is the idea behind amortized analysis. Is that, and it's not like I can't just like apply this willy-nilly. It's one thing that I'm using is that I had to call, I don't just get to, I know that if I've gone from 0 to size 32, I know exactly what's happened. Yeah.
So you're basically taking the average of all of the runtimes of each step?
Yep. And I want to keep this straight. So just because we are doing an average, we're still talking about a worst case. Really, we're still talking about a worst case runtime. We're just averaging over n calls of our add method. So called add n times overall big O of n, so O1 per add. And I would say this is definitely kind of a subtle thing, and sometimes it's easier to understand by actually looking at rather than just trying to get an intuitive understanding, looking at the details. So if you want to look at the details, I point you to those in the book, but I'll also just take some screenshots and attach those to this lecture so that if you don't have the book, you can look at those. But basically, the picture to have in your head, I would say, is that, so we can do this accounting, this kind of fancy accounting, where we say we charge this runtime for this big guy, we charge it, we distribute it over the little guys, because there's always enough little guys to distribute it over. But let's look at our incremental strategy, right? We have to resize so frequently that there's not enough little guys to distribute my runtime over. So this bar, so this is every third resize every third add, right? Because my tall bars are happening every 1, 2, 3, right? And so you can see how these bars are getting taller, but the space between them is not getting any bigger. And that is the key to why the incremental strategy is not going to give us a big O of 1 amortized runtime. It's going to give us a big O of n amortized runtime because we just don't have enough little guys to account for our tall bars. All right. Okay. Let's double check that there was nothing else on the plan. Nope. We got through it. So yeah, I'm going to add that to the lecture page. Let me know if you have any questions. I know Project 4 has some challenging algorithmic bits, so ask if you have questions. You have to go? Okay. You can, if you Discord, yeah.
Do you know if the computer console is open tomorrow?
I don't, but on Discord, and I should have said it in class, I'm going to actually plan on have extra office hours there tomorrow. So I haven't heard from anyone that these were bad ones, so I'm going to do 11 to 12 and 3 to 4, I think they said.
Okay, sweet.
Yeah. Let's see. I'll double check. Course announcements. Yeah, 11. I'll be there 11 to 12 and 3 to 4. I don't know if the TAs will be there.
Okay.
Probably not, because my guess is they get the day off.
None of them are work out, and I essentially broke it up into where we try to reading in like a function name.
Yeah.
I was just wondering that I might go. I want you to write up like function name and then either an action, like function name call, function name call. And if it's calls, you just skip the next. I mean, I think it would work theoretically, but like, is that how you do it, or do you just look up 3 pages like this?
Yeah. Okay. So calls. What's the 3? Okay. Calls.
Or it's a function. Does it reading for each character? So it might be AD.
Oh, I do think that
Because
I
it seems
might not
like
have
you
done-
more describe like A calls or A halts, and if it calls, then push like the next one in. If it halts,
Yeah.
then pop the last one.
Yeah, I think.
That's how you work out.
Yeah. But then there is, it's not, at least the way I did it, it's not that elegant because you have to deal with, if it's a calls, then you have to deal with you have to read it in another extra strings, like A calls B, but A halts doesn't have that third one.
Right, except I was thinking 3, because you can reference the next one with just s.next within the while loop struct.
Yeah.
That's what I was wondering if that was like, I don't know.
I mean, I guess I'm not, I'm not really
like-
sure what you're asking.
So if you do it step by step, you can do it with like keeping track of 2 strings, the previous one, right? If you do it your way, and keep track of 3 strings, you keep track of A calls B. You have to know that one. Which then you waste a spot when you do like A halts, because then you get A halts something else, but you don't really know what the other one is. But instead of keeping track of 3, with the A calls B, you can keep track of the third one B by saying like s.next. Make that work?
Possibly. I guess I probably just have forgotten what I said in the, let's see, Project 4. And Project 4 start. Okay, this is in call stack. Okay. Oh, wait, where did I say? Where do I have this description? In the
Just on the
project
third
description?
floor, yeah.
Oh, okay, not in the code. Might as well. Okay, so call stack validator. So wait, you can represent the call stack using the stack, pushing functions onto the stack as they are called and popping them as they are halted.
Right.
So
I don't know. I think I can get it to work out.
yeah,
No.
yeah, I'm sure you can.
So when you're increasing the array, the incremental will be faster at smaller amounts, right?
Yeah, possibly. Let's see.
Like if you were incrementing by like 20 or something, it would be faster than the double at first. With the amortized analysis.
So, well, I guess, yeah, because it would call less frequently, maybe? Is that what you're saying? Like,
Yeah, because it called less frequently at first.
yeah, like if you started it, yeah.
So then you just have to know what you don't use really. So you might use an incremental.
Yeah, if you, well, I mean, but the thing is, if you have a max size, then you could also get, you could just start with an array of that max size.
Yeah.
But if you don't know how big it's going to get, then,
Probably just double.
yeah. Because, yeah, so basically, like, kind of what you could do mathematically is for any, you tell me any, like, increment that you're going to do, and I can give you a size of an array that I'm going to eventually need, that it's going, that the, like, number of, that after that point, the number of, the runtime of the add method will be linear, on average, like averaged across those, yeah. But yeah, it is true that, like, for the small numbers, it could be faster.
Okay.
Yeah.
So to clarify on the slide before that one,
Mm-hmm.
so are we saying that when it doubles, then the runtime is big O of n?
So yes, it is. Yeah. So the doubles are basically big O of n runtime.
Mm-hmm.
We could think of it that way, or we can be even more specific, and we can say that when it doubles, the runtime, like, it's proportional to what you are at right now, but
Mm-hmm.
but big O of n would work.
Because are we saying per add would it be big O of n divided by n? So that's why we're saying it's big O of 1 per add.
So actually, we say, I may have actually misspoken there. So basically, we're going to say that, like, all this blue area, like, if you add up all the blue area,
Mm-hmm.
it's actually big O of n for whatever n we're at. Like, we're at 16.
Mm-hmm.
It's order of n size. So, like, if I were to think about, like, tipping these over, kind of, like, tip over this guy and use this area,
Because if we cut that big one into eighths, then we'd have those 7.
we'd have, like,
We'd
yeah.
have those 7, and then we just have one extra block.
Yeah, sure. And so we'd really just have this rectangle. And, like, same thing. Take this area and distribute it over this. Take this area and distribute it over this. And that's how we end up with this rectangle.
It's because it's big O of n's constant, so it's just
Well,
the same size rectangle.
yeah.
all the way
Well,
through.
so it's like, overall, like, the time we've taken is proportional to n.
Mhm.
Like, we've taken, if this rectangle is, like, 4 tall, like, say it's 4 tall. And we're at 16, so we've taken, to do 16 adds, we've taken 4 times 16 time. But then we say to ourselves, well, we've done 16 adds, so I'm going to divide that by 16, because I've done 6, I don't want to say, because I want the runtime for 1 add.
Yeah.
So that's why we then divide it by 16.
Yeah. Okay.
Yeah.
Like if you added 20, then it would just be 20 bucks.
Yeah, and I just did. Yeah. Because that's what you had on your program, and then for mine.
doesn't sound like fun. Oh yeah.
And then for mine, I just did.
Maybe if you want the traction, you can do
I just did the string.
I'm more nervous because I want to write
Hey.
it. Oh, that's fair. Like that might be worth it.
Well,